We've got to kick off. We've got to kick off because I always take too long anyway. Thank you. Well, welcome to May's Bath Astronomers session. And this evening we've got Dr. Penny Wozniakiewicz talking to us about impact cratering in the solar system. You mustn't mess with Penny. She does have a huge gun at work, which can fire things at many thousands of kilometers per second. So we're going to find out all about that going on. But no more ado. Yay, found the right button. Yeah, it's June coming up. It's when I talk about noctilucent clouds and things, as if there's nothing else interesting in the sky. But noctilucent clouds are very interesting, but there's lots of stuff out there. And if you keep watching on WhatsApp or Facebook feeds, you see all the stuff that Roger is regularly snapping. So the sun is changing on a daily basis. We've got lovely moon shots going on. And actually, there's lots of colourful stuff to see up there. You concentrate on globular clusters, double stars and things. So it may well be summer fetes and fairs and fun, but you can also enjoy your astronomy. And as Mike tells, actually, it's a good time to hone your kit in terms of telescopes and things like that. If there's a bit of kit you just hadn't really got used to over the winter time actually using, then it's a good time to get that kit out, reconfigure it, actually sort of get used to using it. I prepared this slide 2 days ago. It's wrong. Our membership is now 129. We've got 2 extra members that came in on Monday or Tuesday, I think it was. But there's loads of ways to contact us. If you feel not involved, then just use any of these resources or just give us a ring. Just come along to any of our outreach or any of our regular sessions. Okay, so what have we been up to this month? The newsletter's come out, but there's also weird flying saucers landing in Moncton Combe. So this is the attempt here over on the left-hand side to make the 16-inch Newtonian Dobsonian telescope. Newtonian Dobsonian. Oops. Can someone go and answer the door, Jade? We've got someone knocking at the door. Oh. Yeah, I can hear it. It's really a pain. Each of the components weighs over 25 kilos to put together. So you can easily get a bad back if you try and do it yourself. And as people have experienced trying to put it together with me in the dark, I shout a little bit when you're doing it wrong. So apologies to anyone I have shouted at when you're doing it wrong. We're clubbing together with Moncton Combe to do a sort of storage shed on the side of the observatory in Moncton to actually have it permanently assembled. So open the doors, wheel it out, and it'll be on these tracks. And you just wheel it down to the bottom of the track and just start using it. Compress it again because it's a little telescope, and then just wheel it back into the shed and you'll be done. Okay. Hello. I've been out and about, and this is good because this proves I do change my tops occasionally. So I did the talk at the Pint of Science at the Saracen's Head. And so I was talking about Cecilia Payne-Kapotchkin, which if you've read this month's newsletter, you know there's an article about Cecilia in there. I promote 2 people wherever I go and talk, Alexander Herschel from here and Cecilia Payne, who goes Cecilia Payne-Kapotchkin. So that was fun, and I got a free glass. Although some people would consider talking for 40, and actually I was only about 20 minutes talking, so it wasn't too bad, but that's still too much of an effort to actually just get 1 free glass. But I love free glasses, so I thought it was great. We also did Ask an Astronomer, so you see some of the famous faces around here who helped out, and essentially Emily here was filming us as we answered questions that had been sent in by some of the local schools, kids. So Merrick helped out, Steve helped out, Roger helped out. Just be aware, if you'll buy any of those uprights, if you just make sure you don't knock them, that would be great. And actually, if you came here actually it's this week, it's been playing all this week. Our videos, rather embarrassing, are playing the Star Vault on repeat hour after hour. And Joe Middleton, who runs the place, is sort of saying, yes, he's very used to our voices now. As we explain sort of the smell of space, how stars are born, that kind of thing. And it's been really quite successful. And they've asked us actually if we can do it again. Sort of like keep refreshing it every year or so. So we might have more in our group of illustrious people that don't mind being filmed as talking about astronomy. That was fun. We've also been out and about. Roger has been helping. I'm not sure what Roger told this young lady, but she was quite shocked. It was actually the first time she'd seen the sun, and she was just remarking how amazing it was. And she just moved away from the telescope just for that second, where she was going, "Wow!" And I just caught that snap there. So, and it's good. I think we've done one this month. We did one back in April as well. So the sun is out. Here's proof, if you needed it, that we've got the telescopes. And for those that haven't seen us before, we just bung the telescopes up in the middle of town or in the parks and just invite people to come and look at the sun. This is kind of what all the interest was about the 8th of May. This is sunspot group AR3664, and there's little flashes and things, and those are the coronal mass ejections. There's a series of about 7 to 9 of them that occurred in sequence. And although this is the SDO pictures, the Solar Dynamics Orbiters pictures, it did mean that a couple of days later, something weird on the 10th of May happened in Bath and all over. And we started. So this is just a gathering of some of the images that were shared on WhatsApp from members. So hopefully this is the kind of thing that you also got to see. Now, all these have been, I think everyone's slightly hit the saturation on it. So this isn't what you would have seen visually, but you in Bath, but we actually got better further away. Then and you dark adapted, then it did come out, and maybe you saw some of the photos and backdrops that people have got. So this is more toned down. You've got the colours coming through here. You've got some pinks in here. You've got some greens. You've got some purples in there, and some spectacular ray sort of formations coming down as well. So lots of lovely images. This does look like a comet. I think this was Jonathan's photo, but we reckon it's an EasyJet coming into Bristol International. So that's that one. But it's his best comet shot he's ever taken. Sorry, Jonathan. Okay, so loads and loads. You can see everyone was just clicking. And the WhatsApp group worked wonderfully that night. It just absolutely wild. So if you ever said, why want to join a WhatsApp group? It's because of moments like this and everyone sharing it. Because a lot of people, if you check the WhatsApp group, were giving up. Around about 10:30, they were going, oh, nothing's happened. Should I hang on? 11 o'clock, they're getting a little bit, And then it kicked off. And actually, I was one of the people that walked back to my house. It kicked off and I came back out again. So there's my little admission. What else has been going on? We've had Euclid and some lovely high-res photos. This is M78 near Orion. So if you've got a really good sort of photo setup, this is the kind of thing you might get from the back garden. If you've got a few billion, then you can get this one. So this is just the top of just that bit up there. Okay, so some lovely little bits of science coming along as well. And hooray, Voyager is now working again. Not all of its 4 sensors, 4 instrument packs, but 2 of them are now working. They worked out what part of the sort of data computer had failed. I think it was 256 words within it had basically just wiped out. So they worked out, so if we take this bit of program and move it around and miss that 256, that area, then we can get it. They rebooted it and they started getting information back from the central computer, and then they managed to reconfigure and get it from the 2 instruments. So I think they've got to recalibrate the 2 other instruments and they'll be back to normal again. So it's been out for 5 months or so, but they managed to work out how someone programmed a computer back in 1972, 73.
How long would it take to get signals out to it?
It takes 22.5 hours to get out, and then you've got 22.5 hours to find out the answer. So it takes nearly 2 days to find out if you fixed it. So press a button, come back 2 days later, and you'll find out if you broke Voyager or whether it survived. And last month, our new astronaut, Rose Coogan, Dr. Rose Coogan, she sort of qualified at the end of April. So that was great. Normally there's a bit of a lull then after Europe's got 5 new astronauts. So that makes the entire pool now 11. So we actually got to announce that Sophie is going to fly. I think she's French and Raphael's Belgian. She's going to fly in the spring of 2026. And she's going to be the first of what are called the hoppers. that group of 5 candidate astronomers, astronauts from ESA. They're called the Hoppers. She's going to be the first. He's going to go towards autumn of 2026. We tend to be last in the queue for spots on the International Space Station. So Rosemary, maybe 27, end of 27, early 28 is when she'll be flying. So it's going to be another 3.5 years before Rosemary probably gets a seat. But we never know. But it's good news that they're already planning it in and announcing those. So we'll see how that progresses. And looking forward to next month, then hopefully Starliner is actually going to launch. Fingers crossed, Boeing will actually get this thing off the ground. Buzzing valves, leaking helium from pressurization systems for thrusters. These two, so this is Sunny and Butch, they went into quarantine, gosh, when was it? 2 weeks, halfway through, or 3/4 of the way through April, they went into quarantine, and they're still in quarantine. And hopefully, it's going to be about another 2 weeks before Starliner actually launches. It could be the end of next week, potentially. So a week and a half's time, they could launch for the first time on Starliner. So I wouldn't want to be them stuck in quarantine for such a long period of time. This is stacked. So this is Starship 4 is stacked and ready to go. So it's just when they're going to be allowed to launch it to see how that goes. Both went through rapid unplanned disassembly on Starship 3. They blew up. So we'll see what happens next time. So yeah. And Roger's actually got a much better photo of it, but when I was doing this was the group that was the sunspot group that gave us the May the 10th aurora, and it was AR 3664. It's been redesignated now, but the sunspot group's coming around. As Roger's photos show, unfortunately, it's a lot smaller than it was before. But it grew, it got bigger, and so any of the other things. So it means that some of the cynics who said a couple of months ago they think the sunspot cycle is over and we're going back towards minimum, they were perhaps a little premature. And perhaps it's still hotting up, and maybe even a chance of more aurora for those that missed it the first time around. What we're going to do this month, well, we've got on the 22nd, Saturday 22nd, we've got have the telescopes out the back, and we'll have another solar solstice day. We're going back into schools, so they're reawakening after all their exams and things like that. They're realizing they've got nothing to do over the summer term, so they're phoning me up and saying, can we do some outreach? So that's happening. We've got Fates and Fairs. I can't remember which one this is. Oh, this is Bath Eastern, which is also on the same day, so 22nd of June. So we're sort of double accounting on that, but we've got 2 teams to man those, so that would be great. And if anyone wants me to help fill a hole with concrete in Monkton Combe, just volunteer. Mixing concrete and pouring it into a hole. Is it petrol? There's no electric. Ah, okay. I'll take you up on that. How are we doing on time? Ooh, I'm almost over. Okay, next month we got Pete Richardson. We got loads of stuff coming up. We're still trying to find speakers for, I think we've got 3 more slots next year. But thank you for filling them with Dr. Gemma Attrill, one of them in May, Prim. So thank you for finding her. And we've also found out what happens to my lost emails. They get eaten by Ministry of Defence or whatever it is. Yeah. Okay, so I must shut up and hand over to Penny to give us a talk on impact cratering in the solar system. I've gone for a happy video at the back of world destruction, but I'm sure that's not what the talk's going to be about. It's not going to be about Hollywood, it's going to be about real things. So what's Penny be up to? Well, she got her first master's at University College London, PhD at Imperial College and working with the Natural History Museum. Then jumped ship, went to the USA and spent a good period at the Lawrence Livermore National Laboratory, and then came back for second postdoc position, University of Kent, before getting a fellowship in Natural History Museum. So we'll do these little jaunts to start off with, and you can go back for a bit longer. And then offered lectureship at University of Kent, And now she is head of the Impact Group and Impact Facility, which is a very big title. And it does mean she looks after this big gun. Okay, effectively simulating some of the impacts that we see out in the solar system and on Earth, but with super fast guns and targets. We're going to find loads more out about that. And then this is a bit of a spoiler, so I'd better hand over to Penny now, if that's okay. So if I stop sharing. Hello, Penny. You're on mute at the moment.
I am, yeah. I've managed to work it out this time. I'm not going to start talking just. So you've shown possibly the most depressing video to start there with the destruction of the Earth in the background. I love it. But yes, right. So I've got to find the share screen. Bear with me. Sorry. Okay, perfect. Can you guys see that?
Yeah.
Is that okay?
Yeah, all good.
Okay, perfect. Okay, cool. So thank you for the introduction. Hopefully, oh, I can't seem to advance. Oh, there we go. Okay. Yeah, so the field of impact cratering is quite a big one. Impacts are a universal process and they occur on all of the solar system bodies and beyond in other solar systems, presumably. And so I thought I'd better start by giving a very brief introduction to what impact cratering is, and then look more closely at what impact craters are like on Earth. Look at the question of why it is that we're interested in studying impacts, and then go on to have a look at some of the methods used to investigate impacts, which include, of course, using the two-stage light gas gun in the lab here at Kent. And then I thought I'd just finish off by giving you a few examples of the current research that we're doing here at Kent with our light gas gun facility. Okay, so to start then, a very brief introduction to impact cratering. So what I mean by impact cratering is where we have, for planetary objects, planetary size objects, we're considering two objects. One of them is going to be a smaller object than the other one, and we're having them collide with each other at extremely high speeds. So we're talking anything between a few to a few tens of kilometers per second. So impacts have occurred throughout our solar system, throughout the history of our solar system. And as I say, it's a universal process. It occurs on all of the solar system bodies. And the image that I have here, I don't know, hopefully you can see I'm going to use my mouse to hopefully show what I'm pointing at, because I can point at it with my finger, but that's going to be no use to you. So the images that we have here just show the general process of impact cratering. So we have the initial contact and compression stage, where the smaller object impacts into and makes contact with the larger object. And at that point is when you have a shockwave start, propagation going into what we call the target, is what we give the term we give to the larger object, and then the impactor, also you have a shockwave generated going back into the body of the impactor, the smaller object. And then that's followed by a process of excavation. So you have material being thrown out of the impact crater. That can include parts of the target, so the larger object. Most of your projectile, if we're talking about tens of kilometers a second impacts, is likely vaporized, but you might end up with some pieces of melt, so that might mix with the target material. Once all the ejector has been thrown out, you have a nice crater formed, and then you can have a stage of modification. On planetary objects, we've got gravity, tends to make things settle, move around, so you get slumping, and that's the modification stage of impact cratering. So impact cratering has been going on throughout the whole history of the solar system, and all the way to modern day. And nowadays we have the 8 planets, which I still can't get used to because I still like Pluto to be a planet, but I'll stick with what convention is now. 8 planets of the solar system, but that's not to say that there's no other objects. We've got the asteroids and we've got comets. And when we think of impacts that occur on the planets today, it's from pieces of asteroids and pieces of comets that are impacting into those objects that we're concerned with. So just as a very brief overview as to what I'm talking about when it comes to asteroids, I'm referring to the mainly rocky planetesimals, They can range in size from really small, so a few meters, to hundreds of meters across, like asteroid Itokawa, which was visited and imaged here, as shown by Hayabusa mission, JAXA's Hayabusa mission, all the way to the most massive asteroid, which is almost 1,000 kilometers across, and that's Ceres, which is imaged here by the Dawn mission. So most of these orbit in the asteroid belt between Mars and Jupiter, but they can then become perturbed by gravitational interactions with Mars and Jupiter, bringing them into the inner solar system, and they can also impact with one another, generating fragments, which again can then go through into the inner solar system, and that's when they become a potential threat for us. They can impact into the Earth or impact into the other objects, other planets of the solar system. And then we have comets. So these are the icy planetesimals, typically between about 1 and 15 kilometers in diameter. When they're just dormant, their nucleuses, they originate from, in general, beyond the orbit of Neptune, either from the Kuiper belt or from the Oort cloud. And then again, similarly to the asteroids, they can become perturbed into inner solar system crossing orbits by gravitational interactions with other Kuiper belt objects, and also with the outer icy giants, so Neptune and Uranus. So what we're used to seeing, of course, when we see a comet is with this beautiful tail, which is only produced when they come into the inner solar system. And those icy materials that make up their nucleus start to sublime, go straight to the vapor phase, and then produce these beautiful tails that we're all used to seeing. And of course, one of the issues with that, we're losing the volatiles when they come into the inner solar system, which means that they can fragment eventually. You're losing effectively the glue which binds together the rocky materials that also make up comets, and they can fragment over time. When that's all lost, they let go of all of those rubble pile rocks that are also contained within there. And so those pieces, those fragments, can then go on to impact the Earth or impact the other solar system planets. And then with asteroids, as I say, it's gravitational perturbations, but also you can have impact events going on, sorry. So in terms of impacts today, the likelihood, thankfully, of us seeing something like that video that Simon showed at the beginning happening on Earth is going to be extremely low. We're not going to see a whole comet or a whole asteroid impacting into the Earth, but we can see fragments, because when they break up like this, they generate many more fragments, and those have a higher probability of arriving on Earth. Okay, and when they do arrive on Earth, they arrive typically, as I say, a few to tens of kilometers per second. So typically for asteroidal fragments and asteroids, they'd be arriving at around 18 kilometers a second is the average velocity that they've worked out. And for comets, it's typically around the 20 to 30 kilometers a second, but it can go all the way up theoretically to 72 kilometers a second. So as you can imagine, an impact between two objects traveling at that speed is going to be really energetic, and you're going to see huge increases in temperatures and in pressures, and so you're going to have very impressive modification of the materials that are involved, going from melting all the way to vaporization. So we'll have a look now at some of the impact cratering on Earth. So as I said, large impacts of a whole asteroid or a whole comet are going to be really rare. And in recent history, really what we're looking at dealing with is smaller objects arriving. So these are a few meters across perhaps, and a large number of these will actually end up breaking up and decelerating wholly in the atmosphere. So these will produce these meteors that we see on these whole sky surveys that are being set up across the UK, across the world actually. But occasionally you'll get one which does make it through. We can find meteorites on the surface of the Earth. So for instance, we had Winchcombe recently, which created it did survive, fragments of it survived to the Earth's surface, but it didn't really impact the surface and make a crater as such. So the most recent one where we've had a crater generated would be the Chelyabinsk meteor. So this was back in February of 2013. So we had a 20-meter-ish object came in through the atmosphere. It exploded in the atmosphere and actually created a phenomenon termed as an airburst. But a big chunk of it did actually make it down to the surface and impacted into a lake, an ice-covered lake. You can see here the 6-meter diameter hole that was left behind. And then this is the main mass. So the main mass being the term given to the biggest chunk that's recovered from an impactor. So this is the main mass, which is about 660 kilos, which was managed to be recovered from the bottom of that lake. Larger impacts, though, they did occur in Earth's past, and I just wanted to explain how it is that we go about identifying those, because the Earth is very geologically active, so it might not be quite obvious just looking for impact craters like we can look at on the moon. So what I mean by that is, so one of the things that you would try to find craters by is looking at their morphology. So the morphology of an impact crater, when it's just formed, is largely dependent, firstly, on the material that you've impacted into, but also on the size of the impactor that's come in and hit the surface. So if you've got a small impactor, you generate something called a simple bowl-shaped crater, like the one that's shown here on the left. So very nice and circular, and very nice bowl shape to the depth profile. If you've got something much larger, so we're getting into the above 5 kilometers in diameter, you start generating more complex craters, is what they're termed. And so these will start to show things like slumping of the crater walls, and also a central peak, or sometimes as they get bigger, you may even have a central ring, so like hill-like objects in the center, which is all caused by uplift of the bedrock where the impact has occurred. And then as you go even larger, you can start to generate these multi-ring basins, like the one that's shown here. So this is 930 kilometers in diameter if you go to the furthest ring that can be seen. So these ones have massive chains of mountains going around in concentric rings. So these are all examples that are shown on the moon. So the moon's surface, it's an airless body, and there's no activity, no geological activity going on the surface as such. There's no volcanism, there's no weathering going on, there's no atmosphere to have a nice weather system that can then, chemically modify the surface. So these are really nicely preserved, other than by being impacted by other impacts, so other craters around them. But on the Earth, of course, they get modified over time by the geological activity that goes on here. So morphology alone can't be used to identify craters, most craters on the surface of the Earth. So what we have to do is look for a number of other signs. We can look for gravitational anomalies, and indeed that's the way that the dinosaur killing, potentially, impact crater that was identified. So this is an impact crater that occurs off the coast of Mexico, which is thought to have coincided. It's the right age and the right size to basically be responsible for the iridium layer that we see, that we think is linked to the demise of the dinosaurs. So a massive impact basically killed them off. And so yes, so you can see signals in your gravity anomalies. If you have a simple bowl-shaped crater, then what you'll have is typically you'll have a nice circular gravitational low in your data. If you have a complex crater, then you'll have a circular feature in your gravity data, which shows highs where you've got more compacted and uplifted material in the center. So you can look for signals like that. You also look for the presence of a rock types of impactites, they're termed. So they come in different flavors depending on where you are. So you can have from the least modified, these are shatter cones. So this is where you have minerals in the rock that get aligned by the passage of a shockwave through the rock. Then moving on, you can have something called swavite. This is where you've got the rock of the surface becomes fragmented. It also becomes melted, and you get a mixture of those fragments and those melt beads all mixed together to form this rock called swavite. Or then if you have the target rock completely melted, then you can end up with an impact glass, otherwise termed tektites. So often you'll see beautiful jewelry made out of some of these things, particularly one particular type of tektite called a moldavite, which I think is originating in China. You get these beautiful greens, which a lot of people like to turn into jewelry. But they also look amazing when you hold them up to the light and you get the light shining through them. That's by the by. Sorry, I had a rock collection as a kid. I don't know if you can tell. Anyway, so the presence of impact fragments is also a great clue. So actually looking for fragments of meteorites. So probably the best example of this is going to be Canyon Diablo, otherwise known as a Barringer crater. So you get Canyon Diablo meteorites come from the Barringer impact crater site. These small fragments of metal, iron nickel metal that are basically pieces of the impactor that got spread over the area. You can also look, if you look in detail, if you're using high-powered microscopes at the rocks, you look for minerals, and you look for specific minerals that are high pressure and temperature polymorphs. So what I mean by that is, if you have silicon dioxide, it's probably the easiest example. If you have silicon dioxide, otherwise known as quartz, so those beautiful clear, clear and glassy crystals that you can get. You can often see them in fossil and rock shops because they form these beautiful prisms. So quartz, if you put that under different types of pressure and temperature and combinations of pressure and temperature, then the structure of it will change. The composition will stay the same, but the atoms will rearrange according to the pressure and temperature conditions. And when you have an impact event, there are two particular types of silicon dioxide polymorphs that form. That's called coesite and stishovite. So these are really high pressure, going up to gigapascals, and high temperature phases. So from low to up to 1,800 degrees C temperature. So with those things in mind, those are the characteristics that you're really looking for in order to confirm the presence of an impact crater on the Earth. And so with that in mind, the Earth Impact Database, which you can find online, has recorded 190 confirmed impact craters over the surface of the Earth to date. And in actual fact, I checked this. I've been giving a similar talk and giving lectures on impact craters for quite a while now. That number hasn't changed for at least 6 years. So it takes a lot to get an impact crater confirmed. So I thought I'd just give some examples because there are some great impact craters. I'm such an impact crater person. There are some great impact craters over the Earth, despite them being quite hard to find sometimes. But I thought I'd give you some examples of the most startling ones, the most interesting looking ones. So the first one I thought I'd start with is the Manicouagan crater, which is in Quebec in Canada. So I think hopefully you can see the rough outline of a circle here, very nicely highlighted to us by the presence now of a reservoir that's filled in. So essentially this is a very old crater, over 200 million years old, and the rocks in this particular ring around the impact crater are weaker than the surrounding ones, and they've been eroded away over time, and the reservoir has managed to fill in that now depressed area, that lower region. The actual impact crater itself, the region from the one side of the ring of the reservoir to the other is actually only about 72 kilometers across. The impact crater, though, itself, based on looking for other impact features like the polymorphs and the shatter cones, etc., the impact crater extends out to about 100 kilometers in diameter. And it's thought that it was created by an object that was about 5 kilometers in diameter. An interesting thing about this impact crater, so it was created, as I say, over 200 million years ago. And at this time, the continents were in different locations. We were, I think, just coming out of the phase when we had Pangaea, the supercontinent, where all the continents were stuck together. We were just starting to spread apart, but the Atlantic didn't exist. So we were much closer to Canada at that point. And as a result, we actually have the Bristol impact layer, which is thought to be related to this impact feature. So this is a layer of very small spheres, melt beads, essentially, that were thrown out by the impact event and then settled and formed this nice layer in Bristol. Another example, which I find quite startling, not from the impact crater itself, but from the Earth activity afterwards that has taken over it. So it's Shoemaker crater in Australia, and this is about 1.7 billion years old. It's thought to be the oldest impact crater surviving or identified, sorry, in Australia. It's about 30 kilometers in diameter, and the thing that makes this so startling is that there are seasonal lakes that take over the crater and basically deposit salt when those lakes evaporate, and they give them these beautiful colors at different seasons, at different times of the year. Staying with Australia, another example that I've chosen to show you is Goss's Buff. So this is over 140 million years old. The feature that you can see here, these raised hills, are actually just the central peak part of this complex crater. And it's only about 5 kilometers across, but the actual crater itself extends much further out. If you see an aerial image of this area, you can just about make out a nice perimeter, a nice circular region going around it that's about 22 kilometers in diameter. Then we have Vred Fort crater in South Africa. Hopefully you can see this really nice outline here, these foothills, which show the outer region of the impact crater. This is over 2 billion years old, and one of the oldest, not quite the oldest, but one of the oldest impact craters on the Earth's surface. It's about 300 kilometers in diameter, and it's thought to have been formed by an object that was around about 10 kilometers in diameter. And then finally, I always show this one because I love it. This is the Barringer crater in Arizona in the USA. This is only about 50,000 years old, and it's quite small in terms of, massive impacts. It's 1,200 meters in diameter and thought to have been formed by a 50-meter diameter metal impactor. So this is the crater that I mentioned. We have meteorites surviving in the local area. So that's the Canyon Diablo meteorites, which you can pick up. And that's how we know that in this particular case, it was a metal impactor. For all the other impact craters, we have no idea as to what type of impacting object it was, whether it was metal dominated or whether it was more rocky or whether it was icy. And so those impactor diameters that I've mentioned are very broad estimates based on modeling as best guesses that we can make. I just showed this. So if you visit Barringer crater, which you can, it has a nice visiting center on the outer edge of the impact crater here. You can see the Holsinger meteorite, which is the largest fragment that they've actually managed to find from this impactor. I think it's about 640 kilos in mass. So yeah, wouldn't want to pick that one up. So why is it that we actually want to study impact cratering? So I've already mentioned that it's been occurring throughout the solar system's history, and it's still occurring, and it's a universal process in that it occurs on every solid body throughout the solar system. And it's a major process in the evolution of these bodies. So just from a fundamental reason of wanting to understand more about the solar system and its formation and evolution over time, impact cratering is a really important process that we need to understand in more detail. I just thought I'd seeing as I've given some examples of impact craters on the Earth, I thought I'd give some impact craters on other objects. So here we have the Moon, and the largest impact crater that we find on the Moon is actually in the South Pole, called the South Polar Aitken, which extends approximately 2,500 kilometers across in diameter. So it takes up a big chunk of the lunar surface. You can see from this altimetry data here, the blue region is the lower areas, red is higher, and so the trace of the outer edge of the South Polar Aitken is thought to be around this largely depressed region. Similarly, on Mercury, we see a really nice airless body, which is covered in impact craters. Probably the best well-known, the largest one on the surface of Mercury is the Chloris Basin, which is about 1,550 kilometers in diameter. I'm showing my age completely because when I did my undergraduate at UCL, one of my mapping projects, because we were all given a mapping project, like the geologists got to go out into the field and map a particular location for what the different rocks were. We got given pictures of the planets and told to map the surface and work out what the rocks were. So I remember this very fondly because yeah, I did the Chloris Basin, but I only had half of it because at this point we didn't have the more recent Messenger spacecraft data. So I was really looking forward to seeing the other half of that. Then we have Venus. So Venus has a really thick atmosphere, which is actually really efficient at stopping most impactors reaching the surface of Venus and creating impact craters. From our images prior to radar, so prior to using radar and to actually get a look at the surface, can't see anything or any sign of impacts. But of course, once we got the radar data back from the Magellan spacecraft, we're able to see very nice impact crater features on the surface. Or these are the features that we think are impact craters and not alternatively volcanoes. Then we have moving on to Mars. So Mars again also has impact craters over its surface, and the atmosphere is quite thin, although there is still an atmosphere, 0.06 bars, I think, and so it's able to stop really small impactors, so the dust from entering and impacting the surface. But yeah, you still get meter-sized impactors hitting the surface. One of the largest impact craters that's found on the surface of Mars is the Herschel Basin, which you can see here. Again, altimetry data showing the elevation of the surface and showing that the Herschel Basin is basically this really depressed region here, and has that really nice shape that we're looking for a first clue that we've got an impact crater. We also have really, really fresh craters on the surface of Mars, and very small ones. So thanks to the likes of Mars Reconnaissance Orbiter sending us back these beautiful images, high resolution images of the surface, and repeatedly doing so over the surface, we can actually find very fresh craters. So you have one image where it goes past and there's nothing there. And then on a repeat image over the surface, we find, lo and behold, there's been an impact on the surface. And the likes of the InSight mission, of course, has been on the surface measuring seismic events, linking those two together, the orbiters taking images and the impact event registered by InSight. We've also been able to get seismic data, seismic signals from the impact events, and then image the impact event, the actual resulting impact crater afterwards, thanks to Mars Reconnaissance Orbiter. So the rocky planets aren't the only ones that exhibit impact craters. Of course, we have planetary satellites, all well, many of them exhibiting lots of impact craters. So on Mars, at Mars, we have Phobos and Deimos. With, of course, on Phobos, we have the very well-known Stickney crater, which is on one side and shows these amazing radial features, which may or may not be related to that impact event. Again, I think MMX, the JAXA mission that will be going to Phobos and hopefully landing on the surface, will hopefully find out some more information about that. And going further out, you find lots of examples of impact craters on the moons of the giant planets. So just given an example here from Callisto, one of the Galilean satellites, which has this huge, lots and lots of rings going across the surface. And so this really accentuates the idea that the impact crater that you get is also going to be dependent on the surface composition, the materials that are involved. So it's thought that these multiple rings, the extent of them is largely because of the composition of the surface, with lots of ice being present. Going further out, we have Titan, again in a similar situation to Venus. We have this very thick atmosphere, which stops most impactors from reaching the surface and also stops us from seeing anything, unless, of course, we have radar. And the radar signals that were being backed by Cassini do show evidence of these circular features, which we think are impact structures on the surface. And I always have to show Mimas, because it's always brought up as being the Death Star because of that giant impact crater that we see on its surface. And even further out, going to Pluto and Charon, we see impact craters across the surface sent back in these images from New Horizons mission. And we see interesting features which we don't see on other objects. We see these halos on the surface of Pluto, which seem to be a rim rich in methane ice, and then a center that is covered in water ice. And so we think these are impact craters. And so a lot of work is done to try and reproduce impacts under similar, although it's very difficult to get these kind of temperatures, but similar conditions in the lab to try and see if you produce interesting morphology like this. And of course, on asteroids, we have plenty of examples of impact craters on those surfaces, these lovely airless bodies. And even on comets, we think we have impact craters present on these objects. There have been a number of these kind of shallow bowl-like features on the surface, which were initially identified as impact craters on things like the Rosetta mission's Comet 67P Gerasimenko. I can never say that name. I'm terrible. But yes, but then there's also been some recent work which suggests that these actually might be more likened to sinkholes. After you've lost material, volatiles from the subsurface being lost, leaving a gap, and then you have a sinkhole effect going on the surface instead. So the jury's still out on that one. Really, we just want to go to more comets, I think. Okay, so in terms of, again, going back to why we study impacts then, in terms of understanding the solar system bodies and how they have evolved over the extent of the solar system's history, impact craters are really important because they tell us about the surfaces that are involved. So they can tell us about how the material reacts to impact. So for example, if you have a material that flows, you're more likely to get a very nice smooth crater as compared to a material like ice, which behaves more brittly and creates an impact not unlike something that you would see into glass, with lots and lots of radial fractures and concentric fractures around the impact site. So it can tell us about the surface, the materials that are involved, without actually having to go there and take a sample to learn these material properties. Also, really cool about impacts is when they occur, of course, they throw out loads of material, and it means that you can actually get a look at what's underlying the surface material without actually having to go and dig down. So a great example of this is if you think of Mars, these small craters that we've been able to see the surface when they're not there, and then take an image immediately after they've occurred, and then keep imaging them over time. There have been several small craters, particularly in the northern hemisphere, that have, when they were fresh, they seem to contain bright material, which is largely thought to be water ice. And then over successive imaging by Mars Reconnaissance Orbiter, we've actually seen that material start to disappear as it's subliming because of the low pressure, low gravity, low pressure and warming seasons on the surface of Mars, allowing that material to go straight, unfortunately, straight to vapor rather than going into a liquid phase. Also, a very cool thing about impact cratering, of course, is it allows us to get a rough age of a surface, so relative dating of different surfaces by the number of craters that are on there. So if you have two surfaces, you've got, say, a lava flow over the surface on one side, and I don't know, let's say a sedimentary deposit on the other side. You can relatively date them by how many craters there are on each one. So if this one has more than this one, then this one is older than this one. That makes sense. So they can allow us to do relative dating. In the case of the moon, of course, we have samples from the moon surface, which we can do more precise dating using instruments in the laboratory, using isotope dating. So we can get absolute ages and then link those to different surfaces, and then get an idea of the age of different surfaces and link that with crater numbers as well. So impacts also could have played a very major role in the evolution of life. So the first thought of that goes back to that video that we saw at the beginning, which Simon showed. Impacts during the early solar system are thought to have largely frustrated life, so stopped it from starting, or wiped it out several times potentially, or stopped it from evolving very, very far for a large amount of time. That's because when they occur, you increase the dust content of the atmosphere, which can lead to global cooling and ice ages. You also increase the levels of sulfur and carbon dioxide if you're impacting target rocks that have large contents of those two volatiles. If you have that added to the atmosphere, you can end up with acidic rain, which is really acidic, not just like acid rain from the industrial era, but acidic rain that actually burns. You also ignite wildfires, and you can induce tsunamis. So largely we think of impact craters early on as being quite frustrating to life. And indeed, one of the most famous impact craters, I mentioned it earlier, the Chicxulub impact crater, is thought to be linked with the demise of the dinosaurs. It's around the right size and the right age to be linked with something called the iridium-rich layer. So this is a layer of clay which has a high iridium content. And iridium, when the Earth formed, iridium would have been largely taken into the core. So the surface is quite poor in iridium. So with this rich layer, it's thousands of times more iridium than we find anywhere else. It has to have been brought in by an object that hasn't undergone the planetary differentiation that we see on our own planet. So largely thought of as destructive, but they're not just destructive. So it had been hypothesized for quite a while that impact craters also can be quite a boon to some species, whilst they might wipe out some. So for instance, with the dinosaurs, they wiped out the dinosaurs, but that also led to the mammals taking over and then developing and evolving into modern day man. It's also possible that they delivered materials that are vital to life. So in terms of the Earth, it's largely thought that the Earth, when it started out, was largely sterile. It formed from objects that didn't have much water. The water that it did have was lost during successive impact events. And so really, in order to form the Earth that we see today around us, that has all these organics and water that we need for life, we had to have had it delivered by something afterwards, which we largely credit as being comets and asteroids impacting later and delivering ices and delivering organics, so the requirements for life. It's also possible that they created materials for life. So recently, I'll talk a bit more about this later, but recently we've been doing some experiments in the lab here where we've actually managed to take very simple organics and then create more complex organics by simply impacting those materials. And under the impact, under the shock, they become processed and make more complex structures. It's also possible that they produce habitats that are more conducive to the development of life. So if you think about the impact crater images that I showed right at the beginning, you have a nice crater that's created and you have lots of fracture systems. So for life that inhabits rocks, so lithophiles, we find them in mines today, these fracture systems might be a very nice habitat for them to then colonize and expand from. And they occur at all scales. So another reason why we study impacts is they occur at all scales. So not just the very large planetary impacts that I've shown you examples of, also very, very small. So this is an impact melt bead that was found amongst the Apollo regolith samples that were brought back. And so you can see the melt bead here. It's about 100 microns in diameter, so 0.1 of a millimeter. And on its surface, you can see an impact crater. So this is a melt bead that's been created during an impact event and thrown out, landed on the surface, and then been impacted by another piece of dust, probably a micrometeorite that's come in and hit the surface of the Earth, of the moon, sorry. And it's not just these small impacts occurring on natural things that are interesting. Of course, to us, so going back to the moon, sorry, it's an airless body, so micrometeorites are able to impact this, reach the surface. We don't have a problem with micrometeorites on the Earth because we have this really nice thick atmosphere which prevents them from reaching the surface, although some of them do reach the surface, but they come down very nice and gently. They get decelerated very high up in the atmosphere and then settle slowly to the surface. But what we do have a problem with is in low Earth orbit, where we have our brilliant satellites, providing us with GPS and all the lovely, information that we need. These can be impacted by small particles. I've got an impact. So this is an example here. This is the Hubble Space Telescope. So it had these solar arrays for producing power for the telescope. And when they were brought back, two sets of those Hubble Space Telescopes were brought back on service missions to replace them with better, more efficient solar cells. And when they were brought back, they were analysed in the lab, surveyed for impact features, and we find these lovely, I say lovely, I think they're awesome, impact features over the surface. I'm sure the people who have the solar cells don't think they're awesome, but I think they're awesome. So they can hit our satellites. Now, these impactors, similar to the impacts that occur on the other planetary bodies, they can be natural in origin. So that can be meteoroids and micrometeoroids. So these are typically, largely, I should say, from comets and asteroids also. And it's estimated that about 40,000 tons of dust-sized objects, so that's anything less than a few millimeters in size, they arrive at the Earth every single year, at the top of the Earth's atmosphere every single year. And about 90% of that is burnt up by the atmosphere, with about 10% reaching the Earth's surface very gently, not hitting us, as micrometeorites. But of course, we also make some lovely debris. So anthropogenic dust we generate in the form of dead satellites, upper stages of rockets. And then, of course, when these objects become unstable and explode, they create even more particles. Of course, space is not a very nice environment, especially low Earth orbit. You have atomic oxygen, which attacks the surfaces of spacecraft and erodes them so that fragments break off over time, so you can have flecks of paint. You also generate aluminium oxide spheres every time you perform a burn with your rockets. And all of these debris particles are orbiting the Earth and can hit other satellites. This is a computer-generated model showing the largest pieces of debris in orbit around the Earth, and also included within this are all of the satellites that are still working. And so you can see that it's quite densely populated. In fact, they have a nice set of images from the same models, showing them back in the 60s when there was very little, nothing around the Earth's surface, a little bit towards the end, around the Earth. And then moving on to the 90s and present day, and you can just see the amount of specks, so each one of these representing a large object in orbit around the Earth, the amount of those increases drastically as you get towards modern day. So in order to investigate in order to investigate these dust particles, we have dedicated spacecraft that we put up in orbit, like the Long Duration Exposure Facility back in the 90s. So this was literally just put up into the Earth's orbit and impacted as it was orbiting the Earth, and then brought back to Earth. Back in the day when we had space shuttle and we could fit a large bus-size object like this in the cargo bay of the space shuttle and bring it back down. We also have, talking about instruments that are designed to actually sample dust via impact. So this is another area of impact research that we're interested in. We have the Stardust mission back in 2004, which was sent out to Comet to actually sample dust particles that were coming from the nucleus of Comet Build 2, and then as the spacecraft passed through the coma, these particles impacted into this racket-looking collector, I should call it, on that spacecraft. And then on the Cassini spacecraft, we also have dust detectors, like the Cosmic Dust Analyzer, which was on board, which measured dust and allowed us to get information about the icy materials that are being erupted by the likes of Enceladus, and give us an idea that there may be a lovely ocean hidden beneath the icy surface of that satellite. So I'll now move on to look at how it is that we investigate impacts. So there are really three main methods. So we can either study impact craters in the field, so we actually go out to them on the Earth, we can go out to them and look at the impact craters, look at the rocks that are found there and investigate them that way, take boreholes and then map out the impact crater to understand what's going on underneath. You can also do computer simulations using hydrocodes. And you can do laboratory experiments, which is what we do here at Kent. So studying impact craters in the field is, of course, great for the Earth, but if we want to actually go out and understand cratering on other planets, not so great. If you won't know details about the impactor unless you find remains, which if you're not going there to pick up remains, you're never going to know. You don't know details of the location before there was an impact, so you don't know, you basically don't know what materials you were dealing with before they impacted, so you have no knowledge as to what materials were involved. If you really want to investigate impacts in the field, then the best thing to do is to actually observe them as they occur. So this is rare, but we are starting to see we are starting to be able to observe impact flashes. So there's a whole movement now of observers that are looking at the moon and trying to record those impact flashes that occur when meter-sized objects hit the surface of the moon. And they're also trying to see whether during those impact events you can obtain not just images of the flash, but also spectra from the flash to tell you what materials are there. You can also generate your own impact, of course. So several missions at the end of life around the moon have then chosen to take that spacecraft and impact it into the surface and then observe the impact as it occurs. But again, if you don't go to these bodies first, then you're not going to know details of the pre-impactor state of these materials. So you're not going to really be able to understand the impact crater itself and how it's formed. So as I say, the other method, another method is to use hydrocode simulations. So these are beautiful models. Oh, sorry, I thought that was it was a video. Oh, is it going to run? Maybe. So these are beautiful impact models. I've probably completely ruined it there. It's gonna freeze. Essentially, you model your shockwave in your material, so you know properties of the material of the target and also of the impactor, and you code these into your models, and then essentially you model the passage of the shockwave going through the materials. They're not so useful on their own. If you don't validate them, then you're basically just assuming your theory and how you've put together this model is correct. So really what you have to do is to then perform impacts in the lab at the same scales to check that what you generate in your models is correct. And that's one of the problems, especially for planetary impacts, because in our laboratory experiments, we cannot do planetary scale impacts. So that moves me on to laboratory impact experiments. So there was an image shown earlier showing our light gas gun facility. So this is the Kent light gas gun, which is actually 2 floors down from me right now. So what you'll see here is behind this box. Unfortunately, we can never get a great image that just shows all of the impact. Sorry, all of the impact facility, all of the light gas gun. But essentially, what you have here is on the other side of this box, you have a pendulum. And that is basically our ignition switch. That pendulum, when we press a button, swings and hits a cartridge, standard shotgun cartridge, and ignites, well, basically sets off a firing pin, which ignites the gunpowder that's held in that cartridge. That explosion acts upon a piston, which compresses light gas, which is held under pressure already in this barrel. And then under here we have something called a breech, which this barrel feeds into. At the end of that barrel, you have something called a burst disc, which is just an aluminium disc, which once that pressure, after the piston has compressed that gas to a certain point, once that pressure reaches a certain point, bursts through that aluminium disc. And on the other side of the aluminium disc, we have something called a sabot, which I have a picture of here. It's basically 4 pieces of a polymer, which comes together. And inside there, you can see this hole. Inside there is where we place our projectile. So our projectiles in this hole can be anything from, if it's a single projectile, from about a few hundred microns, so 0.3-ish of a millimeter, up to just over 3 millimeters in size. Oh. Okay, yeah, so that then gets launched down the launch tube through a series of laser light gates to measure the velocity of the projectile, and also through a series of apertures, stop plates made of very thick steel, which stop those 4 containing pieces and prevent them from going down and hitting your target. And the hole in the middle is hopefully where your projectile will travel through. Not always, but hopefully in general, it will pass through that hole and then pass on down into this massive target chamber that we have down at the end, which is 1 meter by 1 meter by 1 meter, so 1 meter cubed. So you can fit, well, you can fit me in it, as you can see there. And that is all held under vacuum, so that we don't decelerate our projectile, and that means that we can basically accelerate particles up to, well, anywhere between a few hundred meters a second, and our top speed is just over 8 kilometers a second, but we don't fire at that. That's not our general firing speed, because if you fire at that speed, we actually start to break parts of the gun. So our typical maximum speed that we do as a daily run is about 7.5 kilometers a second. As I say, we can fire single projectiles, so single particles up to about 3 mil in size. And we also often will fire, if we want really small particles, fire what we call a buckshot, which we keep getting told off for using that term. I'm not quite sure why. It's not scientific, apparently. But lots and lots of small particles, anywhere from a few hundred microns in size, all the way down to 100 nanometers in size. Basically, we can fire it at anything that will fit inside this lovely target chamber. And we can also fire ice projectiles, which is also fun. There are also other laboratory impact facilities that use different types of accelerators. So one example is a Van de Graaff particle accelerator. So with this, you would use you accelerate charged particles, so your projectiles have to be chargeable. So you either choose something that can be charged, or you would coat it with something that allows it to be charged, and then you're able to accelerate that using electric fields. And you can reach velocities up to 70 kilometers a second with these, but you can't select velocities. So it's kind of a bit of a what's the word? Uncertainty about the experiments is what velocity you'll actually be able to achieve. You also can't fire things that are very big in size. So these particles that you can accelerate are typically only a few microns in size. Of course, you can also go out into the field and perform nuclear tests if you really want to experience the kinds of energetic process that an impact is. A large amount of information, particularly about the polymorphs of quartz, for example, were found from these desert test sites, where, of course, you've got these an abundance of silicon dioxide in the form of the sand, and then it was subjected to intense pressures and temperatures and generated these shock phases. But we can't do this kind of experiment anymore. So we are restricted in terms of impact experiments. We are restricted to small scale in the lab. So I'll just finish off then by just giving some examples of some of the work that we've been doing. So I mentioned earlier, when I was talking about why studying impacts, we're interested in impacts because they may have not just delivered materials that were vital to life forming and evolving on Earth, but they may also have produced complex organics on the Earth when these impacts occurred. And so we've taken various ice mixtures with very simple organic contents, and then been able to produce very simple amino acids from those impact events. and a range of other organics, more complex organics than the ones that we put in. So we can show that you can actually use the shock process, the temperatures and the pressures that are generated can actually create organics, so they can synthesize organics in these events. A big amount of work that we did, I mentioned Stardust already. So the mission that went to Cometville 2, it collected these grains as they impacted into the collector, and they were impacting into the collector at 6 kilometers a second. So these materials would return to Earth, and it was hoped that you would be able to analyze those materials and learn more about the comet that they came from. But after impacting into the collector at 6 kilometers a second, they were modified somewhat by those temperatures and pressures that they experienced. Now, Stardust, they did use a material called aerogel, which you can just see here. So this is a really low density material composed of silicon dioxide. It's kind of akin to a foam. And essentially, it was hoped that that would very gently decelerate the cometary particles as they entered into the collector, because it was so low density. And it did do that, but it did still modify them. It did heat up the surfaces. It caused some melting and mixing of the silicate aerogel with the silicate content of the cometary grains. And of course, aerogel is a really nice insulator, so it also kept those warm for a little while, allowing more chemistry to occur. Yep, so we did a lot of analog impacts relating to Stardust, looking at how those particles could be, how those particles are modified by the impact event, and therefore how the particles that came back with Stardust could be related back to the original properties of the comet that they came from. We've also done research to do with the methane that's been identified on Mars. So there's been various spikes of methane observed as various orbiters have taken measurements of the gases over the surface of Mars. And these spikes occur randomly and sporadically, and they're very short term. And it's thought there was various ideas as to how this could have been produced. One of them was that perhaps you had some life form beneath the surface that was producing the methane through its metabolism. The other option was, though, that it could be a byproduct of shock relating. So you'd have an impact and you'd have these minerals, these olivines, and if they were in the presence of trapped water in the form of ice, and then that was released, you could perhaps produce another mineral, which as a byproduct creates methane. So that was some recent work that we were also doing. We're also very interested in studying these small particles in low Earth orbit. And so we're interested in the orbital debris, and we're interested in the natural micrometeorites and what effects they can have on different parts of your spacecraft. So at various times, we've done impacts into different pieces of spacecraft, into shielding, into this one here is a mock-up of one of the windows on shuttle. And we're studying, when you have this impact event, what materials come off, what are the so-called secondary ejector particles that come off. So here we've been doing this is chemical mapping of the surface using a scanning electron microscope, showing the purple is the projectile that we actually fired. So that's the spray of projectile that was then captured by this plate that was 90 degrees to the surface of where the impact occurred. And then you also have this yellow representing the actual glass material that was then sprayed and impacted into this plate. And we've been doing modeling as well to try and understand where the different materials go, what velocities they have. And that's all important when you want to understand, when you have an impact on something, where does the material go, which stuff has the highest speed, which is the most dangerous to the next spacecraft if it goes out and hits another spacecraft. And just also how much debris is made by a single impact into different materials. So it's trying to facilitate spacecraft designers to understand what types of materials are good to use and what types aren't, if you don't want to contribute more to the debris problem that we could potentially have soon in low Earth orbit. We also try to make a lot of interesting target holders. So we've done impacts into hot and cold surfaces, so impacts into ices, because we're interested in trying to recreate impacts relevant to the outer solar system, to the icy satellites of the giant planets, but also hot surfaces. So if you do have an impact on something like Venus, which has a really nice oven-like temperature on its surface, do the rocks behave differently when they are held at a higher ambient temperature before being impacted? Okay, so those are some of the examples that we've been doing here, and I thought I'd finish there because I think I've reached my time limit. So thank you for listening, and thanks for the invite to talk today. And if you have any questions, I'd be happy to answer them.
Well, thank you very much, Penny. I love it when you hear someone who's passionate about their subject, and there's a potential destruction of the Earth, and you're giggling.
Yeah.
It reminds me of those silly questions. My first question I'd like to ask, as people are probably tapping away to get into their chats and comments and things like that, but what's on the back door of that of the light gas gun to stop you going through and basically pummeling the person in the office next door?
Yeah, so there is no office next door, definitely not. Our health and safety wouldn't allow it. But this is a steel door. It's about 3 centimeters thick. And it's really heavy because we had to take that door off not long ago and take the whole, you didn't want to be in our car park at any time soon, because we had to take this whole chamber off to have more ports put into it. So more holes for more connections that we can make and attach various things to our targets. So this is a very thick stainless steel, hardened steel door. So yeah, you won't have anything go through. I mean, you would hopefully also hit your target before you hit the door. That's enough to stop 8 kilometers a second. Of the size of thing that we can shoot, that is. It's only 3 mil, so we're okay.
But I notice you haven't got anything that can do pressure, so you can cool things down. But in terms of things like emulating Venus, you can't do anything in terms of the pressure.
No, so one thing, yes, I haven't mentioned. So there's so many things that we're doing. I never know which one to focus on. So one of the things we are doing at the moment, actually, it's relating to micrometeorites and the entry of micrometeorites through the atmosphere. And so we were trying to reproduce it with the gun. Basically, we have inside the target chamber here, we attach a tube. And in that tube, it's sealed at both ends. At this end by an aluminium piece, and at this end by a very thin capped-on foil. And we seal it with atmosphere inside. So whilst we take this down to vacuum, we keep the tube at atmospheric pressure. And we're starting to work on increasing that atmospheric pressure. So we're going to get up to about 3 atmospheres, I think, is what we're aiming for at the moment. And that's all to do with atmospheric entry. We're just trying to subject a 7 kilometer a second particle to sudden impact into an atmosphere and see whether we create anything interesting in terms of the types of features that we see on micrometeorites when they're collected at the Earth's surface. And we just like doing this kind of stuff. I shouldn't say that. There's no funders in the audience, are there?
So what questions do people have?
A lot of the craters we start.
Yeah.
Okay. A lot of the craters that we see are very circular, but what effect would the angle that the impactor comes in at have?
Yeah, so that's a very good question. So it's modeling suggests that the average impact angle that impacts occur at is about 45 degrees. So coming in, not a nice perpendicular one like we tend to generate in the lab quite often, but coming in at 45 degrees. And so we have done varied angles of impact in the lab. And what we find is that and also with modeling, if you want to scale it up to planetary scales, what you find is that for these impact craters, anything below about 50, so like glancing incidents. So I'm going, if I say 0 is straight on, 45 degrees is coming in at an angle like that, and then 50 is down here. So even more glancing than 45 degrees, then you don't actually see a difference in the shape. You still get a circular outline to your impact crater. You have to be very oblique, coming in at a very nice, very high angle in order to generate a crater that looks elongated. So that's why they're so rare. But you do see them, I should say. You do see interesting, like slug-like looking craters, often with interesting ray patterns. They look like butterflies on the surface.
Thank you, Penny, for a really interesting talk. You mentioned that on Mars there were some sort of newer craters. I wonder if there's been anything spotted on the Moon at all, from old drawings, perhaps from old maps, and we've seen that new craters have formed on our Moon.
So just like Mars, the Moon has lunar reconnaissance orbiter as well, with high resolution imaging capabilities. So I don't know if like me, I always some of my lectures I talk about space exploration and Apollo missions. So I always highlight all these images that lunar reconnaissance orbiter has sent back of the Apollo landing sites and all of the lovely little trails. So just like with, sorry, I'm diverting there. I couldn't help but think of the Apollo landing sites whenever I say lunar reconnaissance orbiter. But yes, so just like with Mars Reconnaissance Orbiter, we have Lunar Reconnaissance Orbiter, which is able to repeatedly image the surface, and therefore, by doing comparisons, spot new craters, fresh craters on the surface.
Have there been any significant sized ones?
I seem to recall recently there was one that they got really excited about because they spotted a flash, and then were able to, they thought they may have found the impact crater responsible for it. So yeah, and then of course there's the impact craters. So Lunar Reconnaissance Orbiter has been able to see the impact craters and image the impact craters after we impacted things like Smart 1 into the surface. So yeah, so spotting those impact craters as well.
Thank you.
Hi, I think you might have partly answered what I'm going to ask. I'll still ask it anyway.
Go for it.
You implied earlier on that you couldn't easily tell from impact craters what the nature of the impactor was. But we had a talk recently, and you've touched on it, the asteroid that was sampled. We find that some of these asteroids are incredibly friable compared with the ones which are iron and stone. And that doesn't really make a difference on the nature of the impact crater. Is it just sheer energy?
Yeah. So do you mean in terms of if it's impacting into something like the Moon, or?
Yes,
Yeah.
an air body, yeah.
Yeah, so in terms of our impact craters that we do in the lab, where we do see differences between if you have a metal impactor, like a nice stainless steel ball bearing, versus a glass impactor. So what you'll see is that your depth to diameter ratio is quite different. So you end up with the denser objects, the stainless steel will make a deeper impact crater than the glass impactor. But a lot of those impact craters that we create are into metal surfaces, so they're not like the Moon at all. So probably not relevant to that one. But yeah, it's the problem is when you impact into a planetary surface, there's so many other variables that are at play. So if you impact into one area, you might have happened to have hit a fracture in a rock, or you might have, a geological feature like a dike or a sill underlying, which changes the reaction of the rock to the impact compared to somewhere further over where maybe it's dominated by sedimentary rocks with no igneous materials. So the strength of the material can vary from location to location, and it's without being able to land on the surface, take a sample and then plug that information into a model to say, okay, this surface is going to behave like that, this surface is going to behave like that. What can we work out about the impactor from how those surfaces have reacted based on what we know about what they're made from? Without all that information, it's just hard to then make those interpretations about what the impactor was made from.
Thanks.
Sorry, that just reminded me about another question on a personal level. So I've got a tech type from bits that I've collected, which I was accidentally sold as an asteroid, meteorite. But
Oh, tektites are awesome though.
yeah, it's
Brilliant.
very nice. It's really nice. Is that completely terrestrial, or could there be tiny bits of the impactor embedded within it, do you think?
So
Okay, I'm reaching here. I'm reaching.
so tektites are dominated. They're pretty much exclusively molten target rock.
Sure.
But there is a cool thing about tektites. So within some tektites, you actually have bubbles. And those bubbles can preserve a sample of the Earth's atmosphere at the time when the impact occurred. So there's been some really cool research actually being able to sample those gases. I don't know how they managed it, but sample those gases from those bubbles to learn about the atmosphere of Earth at these different times when these tektites formed, which is really cool. Sorry, I digressed there, but
No,
yeah, so tektites are awesome.
Great, thank you.
You've made Prim very happy.
Awesome. Is it a teardrop or a button shape, or does it have any kind of shape to it?
It's got no shape to it. It was very rough.
That's all right. It's fine.
Yeah. Looking at the 190 impact craters around the world, okay, we've got none in the well, very few that have been spotted in the ocean, but the distribution doesn't seem to be random.
Yes, so that will also have to do with the location of the ocean, the movement of the tectonic plates. So it destroys some, preserves some better than others. So it just depends on the geological activity of the region that you're looking in. So they might just happen to be better preserved in these locations. In the ocean as well, it's really hard. We don't really understand the process of impact cratering in the ocean very well. Our models aren't able to model water very well. So when we have an impact crater, when we're doing a model with an ocean above a rocky target, we're never quite sure how well we've done with modeling the water and how it reacts to the impact and how much it stops the impactor reaching the actual sea floor. So in our models, it suggests that a large number of the impactors don't actually reach the sea floor unless they're massive. They just won't penetrate the ocean.
Any questions from our Zoom audience? You pop your mic on.
Do you want me to look at the chat, or can you? Sorry, I shouldn't be. It's me sharing, isn't it? So
there's one person on the chat. I haven't seen what that message is. I'm going to ask on the side actually. Oh, it's okay.
oh, sorry.
That's all right. You were recently on the Infinite Monkey Cage. What was that like?
Really scary. It was fine until I got there and I saw the massive queue of people and they were being kept outside waiting to go in. So they weren't in the best of moods, I don't think, when they got in there. So it was kind of like, yeah, quite scary, quite daunting. And then, of course, I got to meet Jonathan Creek, which was awesome, but also really nerve-wracking. So, because I couldn't call him Jonathan Creek. So, yeah.
Oh, it sounded like a lot of fun. So I think that's series 27. I'm trying to remember, actually.
I think so, yeah, the last one. We weren't actually supposed to be on. It was supposed to be, oh gosh, AI, I think, or machine learning or something. And then the person that they had organised couldn't make it for some reason. They were a very important person and they had to be somewhere else. So they happened to have, the producer happened to have been doing a show about this guy called John Larson, who collected micrometeorites from rooftops in Norway and then around the world. And then we've been doing it recently as well on the cathedral. So they brought us on and they made us their issue.
Well, it did sound like a lot of fun. Any other questions inside here? No? No? See, when I look at the moon, I'm fascinated by looking at the ejectors and the rays, but do the actual rays tell you anything more than the actual crater itself, or how much can you tell from what's happening around?
So the rays will, on an airless body like the moon, they'll tell you something about the energy with which they've been excavated. You can get an idea as to how fast it was going, how much energy was deposited and how much material was thrown out. But again, it's still going to be uncertain. There's going to be uncertainties based on, you know, not having knowledge as to what the surface was made out of. If it was made out of something that was quite you know, brittle, that broke into lots and lots of pieces quite easily, versus into a few chunks that got thrown out. So yeah.
Okay. Yeah. Okay. I'm just going to ask though, because I disturbed you a couple of weeks ago, and you were saying you were writing some grants and
Oh
things.
gosh, yeah.
So what does the future hold in the next few years for the facility at Kent?
So at the moment, yeah, we're moving on from Stardust. So our work with the cometary detectors, so dust detectors, for missions like Stardust, has meant that we've actually ended up being involved in quite a lot of dust detector proposals going forward. So we're at the moment, myself and a colleague who's here, are involved in an ESA what they call it, facility definition team. So we're basically advising on what kind of dust science should be done on Lunar Gateway. So we're involved in that, and that basically involves us trying to do similar experiments to try and calibrate these kind of dust detectors. We're also involved in, there's a mission being proposed to go to Io, so the moon of Jupiter, to actually fly through the plumes, because it's one of the most geologically active objects in the solar system. I think they call it the most volcanically active. And these plumes have been going and continuously spraying out material for estimates range from, you know, like around 6 years, just continuous flow of this material. So really good prospect for actually taking a mission and flying through the plume and collecting dust particles, which they then want to propose to bring back to Earth. So we're also involved in that, trying to do, again, calibration experiments to see how well different materials will be captured in different types of capture media. And likewise, also a mission, several missions are being proposed to go to Enceladus. And rather than bring materials back, they actually want to do analyses of the materials whilst they're in orbit around Enceladus. But it still requires us to understand how these particles have been captured, because all of these missions will end up with the particle that you want to know a lot about having undergone high temperature, high pressure processing by being collected via impact into these target materials. So it's really important that we be able to reproduce that in the lab with materials that we know well, that we think are present. So there is a little bit of guesswork going on in there to try and make sure that you pick the right particles, and see how they get modified by an impact event. And then other than that, we're also working on various low Earth orbit detectors. So that the grant that I was working on last week is a commercialization grant. So we recently had a paper published about how you can detect impacts in space in low Earth orbit using a detector which has acoustic detectors. So it's basically a capped on foil with these acoustic sensors at each corner. So when you have an impact event occur in that foil, they vibrate. You end up with this acoustic signal being measured by these sensors, which can then allow you to triangulate where it impacted and get a bit of information. If you have multiple layers, you can get information about the speed that it was traveling at when it went through. And then what we've done in this recent paper was to actually show that you can also measure a light flash when it passes through, even a thin capped on foil. You can measure a light flash. So the proposal that I was putting in was about trying to create that and advance what they call technology readiness level, to actually be able to launch it with our industrial partner.
Oh, it sounds like you're going to be very busy over the next couple of years.
Try to. Yes, yeah, as with all of these things, which ones actually happen will all depend on funding and time.
Well, I'd like to thank you, Penny, for giving your time to give a great talk. And if people can put their hands together again, thank you very much.
No problem. Thank you very much for having me.